Dear students, now let us see this question. So we are doing some problems on pressure in an accelerated frame. So a rectangular box is completely filled with a liquid of density rho. The box is accelerated horizontally with a constant acceleration A. Determine the gauge pressure at points A, B, C and D. A, B, C at these 4 points we are supposed to calculate the gauge pressure. So already we have discussed that if a system is accelerating or if system is experiencing any acceleration, then pressure always increases in the direction of acceleration. So therefore we say pressure increases in the direction of acceleration. Therefore, as acceleration due to gravity is acting downwards, so in this direction pressure will continuously increase according to rho hg. Similarly, if this is the acceleration of this box completely, then a pseudo force starts acting in this direction. So if this is the acceleration experienced by this liquid, then definitely I can say here also in this direction pressure increases according to rho L into A. So where in this condition H is height of the liquid column and L is the length of the liquid column in this direction. So if I say this total length is L, then at this point pressure due to this acceleration will be rho LA. So this is how in the direction of acceleration pressure continuously increases. Now if I take this point A, at point A, so H is 0, similarly L is also 0. So definitely I can take pressure at point A is equal to 0. Now if I take point B, at point B length towards the left side is 0 because here there is no length onto this side. Now we have only H, so if I consider height of the box to be small h, then definitely I can say here due to this acceleration due to gravity, a pressure of rho hg exists. So therefore pressure at point B is equals to rho h into g. Now if I take this point C here due to the height of the liquid column, rho hg pressure will be existing. That is, this pressure will be existing due to G value. Similarly, from this position, the length of the liquid column in this direction is L here. So due to this length, as continuously pressure increases in the direction of acceleration, definitely I can say due to this length, pressure will be rho L into A. So therefore, pressure at point C is because of rho hg as well as rho into L into A. Now if I study about point D, so here height of the liquid column above this point is 0, so rho hg will become 0. But because of this length of the liquid column L and because of this pseudo acceleration A, here there will be an acceleration of rho L into A. So therefore pressure at point D can be written as rho L into A. So this is how we can distribute pressure in this box which is accelerating. So here this question is based on the concept that if I go inside the liquid column, that is in the direction of acceleration due to gravity, then pressure due to rho hg continuously increases. Similarly, if I move in the direction of opposite to the direction of acceleration of this box, that is if I move in the direction of pseudo acceleration of this box, then also pressure increases according to rho into L into A. So this rho LA and rho hg, they are analogous. So instead of rho, we will write rho here, and here height increases in this direction, and here L increases in this direction. So H is analogous to L. So this is the acceleration due to gravity, and this is the acceleration due to the acceleration of the container. So LA. So these two terms are always analogous terms. Students, now let us see this question. An L-shaped tube is accelerating with an acceleration of A. What should be this acceleration such that pressure at point A should be equal to atmospheric pressure? So if this tube is accelerating with an acceleration of A, so here pressure should be equal to atmospheric pressure. Then what is the required acceleration that we are supposed to find out? So if let us see how we can proceed. Already we have discussed that inside the liquid, if I move in this direction, then this is the direction of G value, then pressure increases according to rho hg. Similarly, if this is the acceleration of the container, then this will become the pseudo force experienced by the container, that is the liquid in this container. So therefore, if I move in this direction, then pressure increases according to rho into L into A. Now according to this one, if I write pressure equation, this is how I can write. So let it be the first method of solving this problem. So we will discuss the second method of solving this problem also. So here pressure is atmospheric pressure, that is what he gave. Here pressure should be atmospheric. Plus now if I move in this direction, then here pressure increases, and if I take a point C here, then here pressure should be equal to pressure due to atmospheric pressure plus pressure due to rho LA. So P atmospheric plus rho LA, because as I am moving in this direction, pressure increases due to this length of the liquid column. So this pressure should be balanced by this height of the liquid column and as well as atmospheric pressure, which is also present at this point B. So this should be equal to again P atmospheric plus rho into capital H into G. So this is how I can write. So P atmospheric and P atmospheric get cancelled, rho and rho get cancelled. So A is equals to H by L into G. This is how I can calculate the acceleration such that here pressure should be atmospheric pressure. Now let us see the second method of doing this problem. Second method is, we will use a method which is called as modified manometric equation. Modified manometric equation. So in this equation, so we know that here there are two accelerations which is acting. So one is acceleration due to gravity, and another acceleration is pseudo acceleration A here. So therefore, if I take resultant of these two accelerations, then the G effective value will be in this direction. So G effective will be equal to square root of A square plus G square. Now these two surfaces, if I draw a tangent to these two surfaces, so if I draw a tangent like this, then I see that perpendicular to this tangent, G effective value will be acting. So this is the direction of G effective. Now again, previously how we have used the manometric equation, in the same condition we will follow now. So I will start from one end of the pipe and I will reach to another end of the pipe. So here pressure is PA, which is equals to P atmospheric. Now as I am moving in this direction, so because of rho LA, pressure continuously increases. So therefore I add the pressure, which is equals to rho L into A. From here to here, length of the liquid column is L. Now from here again I have to move upwards now. If I move upwards, then pressure will be due to rho hg. Because of acceleration due to gravity, this pressure will be acting, and as I move upwards, pressure decreases. So therefore I will write rho capital H into G. Now I have reached the other end of the pipe, and here pressure will be again equal to atmospheric pressure. So if I cancel these two, then I will get A is equals to H by L into G. So in this method also I can calculate very easily by constructing a manometric equation. Now let us see this question. A barometer kept in an elevator accelerating upwards reads 76 centimeters of mercury column. So what is the air pressure inside this elevator? So the atmospheric pressure which is present in this elevator, this we are supposed to find out. So if this elevator is accelerating upwards, then a pseudo force A is equal to 2 meters per second square. It starts acting downwards, and acceleration due to G is also acting downwards. So total effective G value will become G plus A. Therefore, pressure due to liquid column we know how to measure. So P atmospheric, that is if I take here one point and here one point, if these 2 points are at the same level, then P atmospheric should be equal to rho H into G effective. So P atmospheric is equals to density of mercury column is 13,600. Height is, it is given that it is showing 76 centimeter. So 76 by 100, and G value is G plus A in this condition. So therefore P atmospheric, that is pressure inside this lift, is equals to 136,000 cancel into 76 into 10 plus 2. So if I do all this calculation, then I will get 1.24 into 10 power 5 Pascal. But we know general atmospheric pressure, that is pressure at normal conditions, is 1.013 into 10 power 5 Pascal. Now this value, if I measure this value, definitely I can say the pressure inside this lift is greater than atmospheric pressure. But still it is showing 76 because the effective G value has increased in this condition. So it means that weight of the liquid column increases. And because of that increased weight of the liquid column, even 76 centimeters of pressure is enough to measure this much of pressure.